Okay, so thank you very much for the invitation. I'm very happy to be here, and I'm going to present you a general overview of one field, which is superconducting electronics. So far, this field was like in niche applications, like for a very long time it has been niche applications for geophysics, for example, or for scientific research. But it has never had a lot of applications in the real life, and it is going to change. It is going to change. There are a lot of projects now on superconducting electronics, running especially in the United States, Japan, but also now China since a few months. So there is a lot of money put on this activity. In fact, something like about 1 billion euros over. When you add China and the US, so it's quite a lot of money, and it is because this technology relies on some devices that we call the Josephson junctions, which have been discovered or at least theorized by Josephson in 1962, and you see 62, 2019, it's about 50 years of development, and it corresponds basically to the development of semiconductors that were, the transistor has been invented in 1946, and the first small computer that you can buy in the shop and solder yourself was in 1981. So it took about 40 years, and 50 years after we had these nice first good computers. So we are about the same time scale, 50 years of development between the invention of the device and real applications. Of course, we started about 20 years after the transistor, so we are 20 years late compared to semiconductors. The time has come for application, and I would say it's a very good time for students to go in the field, because there will be some jobs, there are a lot already of jobs available in this market, and we don't have enough students to go in this field. It was not yet the case 5 years ago, where this field was like what we call the Death Valley. When you have a technology which emerges, you have science, a lot of emulation with science, and after it's not ready yet for application, so there is a bit of desperation for a few years. So we had this desperation, this Death Valley, which lasted about 10 years from 2000 to 2010. And now we are ready for real applications. Most of the problems have been solved, and I'm going to give you a general representation of this electronics. It's really an electronics which has all the same features that in semiconductors. You can do analog, you can do digital, and you can do in very different. You can use it in different fields of application. It can be for voltage standard. It is the case already for a long time. For radio astronomy, it's also a case for a long time. All the best receivers in sub-millimeter astronomy use superconductors based on the Josephson junction. Medicine, it's used also with quiz, I'll talk about it. Security, geophysics, and now we have digital coming and nearly ready. And we are going to be able to combine analog and digital to make very complex circuits, like we call mixed signal circuits. And this is now possible. It was not yet possible still 10 years ago. So just to tell you where we are just, in fact, in Europe in general, there are not a lot of groups working on this field. I mean, with applications, there are a lot of research on fundamental level, but not a lot for application. So there is a few groups in Germany, and in Holland, and in France mostly, and in Italy mostly. So we are in the French Alps, close to Geneva, between Torino, Geneva, and Lyon. We are along between mountain and lake, and we have a small university with. We have 4,000 students on this campus. There are 15,000 students total. We have 3 campuses, and there is also a lot of technological park with 180 small companies for applications of all kind of innovative things. So all these activities in Europe, we try to federate our activities between the different groups working, and we have a list of institutes which are where we know each other very well, and we try to organize things so we can push this technology compared to other technologies like semiconductor, where there are a lot of people involved. And to give you an overview of about what we can do with Josephson junctions, which is the equivalent of the transistor. As I say, we can do metrology with voltage standard to calibrate all the instruments. We can do spectroscopy for physics or for security application. We can do medical application with magnetoencephalography with quantum magnetometers based on superconductors, geophysics, magnetic field imaging as well, and radio astronomy with heterodyne receivers mostly, and security with imaging system. So in all these cases, most of the time the Josephson junction is the main component which is used. It's used in different modes. I will just give an overview of some of the operations of this Josephson junction, and I will focus a bit more on the digital part after. So the Josephson junction, this is an example of what we have in the fabrication foundry in Europe, which is in IPHT in Jena, Germany. This is a process which is certified ISO 9001 to fabricate junctions. So you can see here it's a ground plane superconducting, the base electrode. There is another superconductor and the junction is just here. And you can see here a resistive layer which is in parallel with the junction. I will explain you why after. The junction is here, the resistor is here, and you have this resistor in parallel. If you follow the positive bars, if you go this way, there is a VR here and you come back. So this barrier is about a few angstrom thick, so you have quantum tunneling, and this is all this good property of the quantum physics used in this case, which we use for electronics. So to give an example of an application, it is one of the voltage standards done by Superconducting in Germany, in Vienna. And so you can see an array of a lot of Josephson junction. This is an analog device, even if, at least in the principle of operation, when you send a microwave here with this antenna, then power is spread here, and we can show that when you put a certain frequency on this array, you have some voltage steps on the current voltage characteristic that are given with fundamental constants. So it's a fundamental way to measure a voltage, and it is used to calibrate all instruments, all electrical instruments that you use or you can buy in the market. So basically, Josephson junction have been used first as analog detectors. How they look like? If you want to see the properties of the Josephson junction, you can just measure your current, what we call the current voltage characteristic. So when you start to put a current in the junction, there is no voltage. It's one of the properties of superconductors, right? No voltage with current. When of course it's cooled below the critical temperature of the superconductors. For niobium, typically it's below 9.26 Kelvin. And when you reach a maximum current, then you have another current, kind of current appearing here, which is connected to the gap voltage. If we try to make a simple analogy with semiconductor, you have these two superconductors, this electrode, this one, insulator is here. This is the level, the state, intensity of state of the level of energy levels. And when we cool the superconductor, we have condensation of these electrons in two pairs. And not all, but most of them are condensed on this at the Fermi level here. And we can show with quantum physics that we can have a tunneling without any voltage appearing. This is what we see here. Of course, the number of Cooper pairs, which are bosons, by the way, they are not fermions anymore. The number of Cooper pairs is limited by the number of electrons, by the structure of the superconductor. And when you try to pass more current that the superconductor can stand, then, of course, you have a normal electron tunneling, and you see that the gap voltage, basically, this part is due to the fact that when the voltage, you change the voltage between these two electrodes, you can see here and here, then you see that this, you can break Cooper pairs into quasi-particles, two electrons, say, and these electrons, they can tunnel normally, but resistively. That's why you have a resistance here above the gap voltage. This is one of the properties of this junction. So theoretically, this density of state here close to the gap is infinite, which means that the nonlinearity here is very strong compared to semiconductor diode where you have an exponential variation. Here you have a very strong nonlinearity, which means much better properties to do conversion, frequency multiplication, all processes that use nonlinearities. And okay, so I will not go too much on the detail. Just to give you an example of this junction used as detectors at TRS frequency, I should have told you that here, this gap voltage is about 3 millivolts. It's much lower than the 800 millivolts of semiconductors. So the gap frequency is typically 700 gigahertz. It means these junctions have quantum properties in the sub-millimeter TRS range, while diodes, normal diodes, they have gaps at 0.8 millivolts, basically, which correspond to infrared. That's why we have so good cameras, right, and infrared cameras with semiconductors, because they have quantum properties in infrared wavelengths. Here we have them in sub-millimeter TRS range, and this is the only technology, only microwave, only frequency range which is not yet totally covered by instruments because of technological limits, just because of that. It's complicated to develop. So we have a device which is well adapted, well suited for this. And to give you an example of how they look like, this system, this is an antenna, a butterfly antenna that is put on a waveguide. This is an antenna. You see here there is a small spot. It's one Josephson junction. And this is just a detector of TRS radiation. And this is just a structure to this junction. It has two superconductors very close to each other. So it's a very high capacitance. Then it shunts the high frequency. If you want to remove the shunt, the frequency, the capacity, the shunt back because of the capacitance, what you need is to resonate the circuit with an inductance. And the way to do that is to put an inductance in parallel. And this is just a distributed circuit to make an inductive part here. So it means at the frequency of operation, this system has no capacitance and doesn't shunt input signal. Then, since it's not shunted, you can detect it and use it for, in this case, for astronomy purpose. So you can see here, this is the input of the wave at about 400 gigahertz in this case. The mixer where the junction is here. Here you have mechanical thing to adjust impedance, because the impedance match is very difficult at 400 gigahertz. And there is also coming with the signal, there is a local oscillator, so we have two frequencies coming with a slight difference of, in this case it was I think 8 gigahertz, 24, yes, 8 gigahertz. And then you get the difference of the frequency when it's mixed by the nonlinearity of the junction. This signal at 8 gigahertz is amplified with a called 4 Kelvin low noise amplifier, HCMT amplifier. And then you can use this signal to put it on a spectrometer to measure all kinds of things. So this thing was installed on a cryostat a long time ago. It was the first flight of a superconducting receiver in the world. It was a precursor of this Herschel satellite. So we tried with a small telescope. You see it's a 60 centimeter telescope. You see the spectrometer here, the autocorrelating spectrometer, and it has been sent. It was done by the European Space Agency, the French Space Agency, the Swedish Space Agency as well, and some Swedish company. And we had, with this, we flew and we could, the objective was to detect oxygen in the molecular cloud. So it was the first test of a superconducting receiver for analog applications. After that, there has been some satellites like Herschel. You can see here the cryo cooler, the helium tank of Herschel satellite, and the satellite is here. It was launched in 2008, and it is so far the best telescope for astronomy, radio astronomy, which has been sent in space. It worked a few years, and astronomers are still using data. It's not finished. They are not finished with processing the data 10 years after the sending. So these superconductors are used always for very high quality experiment, when you want sensitivity, when you want ultimate performance. And another example of application of of this detector is also to detect they're also using detectors in astroparticles, for astroparticles and in particle physics. And well, I just show here an example. It's not about the receiver itself, it's about the use of superconductor in the LHC at CERN, where all the magnets are made also with superconductors. So we can use this device from the infinitely small to the infinitely large experiment. One application of this, another application of the Josephson junction is to use them as magnetometers. It's like in optics, right? In optics, you know that if you have a slot here and you send a monochromatic light, you have diffraction pattern with light intensity. It's all well known, right? Since with superconductors we have bosons, we have exactly the same properties with photons. We can also do diffraction and interferometry. So the analogy consists to replace the phase of the electric field by the phase of the wave function in the superconductor. The light intensity, this is the critical current of the Josephson junction, which is the equivalent. And for the diffraction direction, when you change the direction, you change the phase, right? And you can do the same with superconductors. When you put a magnetic field, you change the phase of the wave function. You can see that from a quantum physics equation, from the very basic equation of quantum physics. So finally, you can do the same with superconductors. You know that in optics, if you use this Young experiment, you have two small slots and you have interference. And you can do the same with the squid. You just replace the two slots by two Josephson junctions. And the phase, instead of being the phase of the electric field, is the phase of the wave function. And when you put a magnetic field, you also have a diffraction pattern like or interference pattern like this one, except here you have the critical current, and here you have the magnetic field as this axis. So we use that to do very nice magnetometers, which are used, for example, to study epilepsy on the brain, where you can put these very sensitive squid magnetometers, two junctions with an inductance. The real squid are not like that. They have a much bigger loop. Here we have a very small loop. This was just to do some tests. And you put these magnetometers on the helmet. You pull the helmet with helium. Of course, you insulate the helmet to avoid some problems with the person. Otherwise, you don't need anymore to do any medicine. And you can see the interior of the helmet with all the detectors. So these are now commercial products, and they are used for a lot of in many different fields. These sensors are so far still the best to do the most very sensitive application. When you do this kind of experiment, you need to be in a magnetically shielded room, because otherwise you get all the perturbations. And so the sensitivity is an advantage, but it's also in the same time a problem, because if you are very sensitive, each noise, every perturbation makes you problem. So finally, these systems are sensitive, but they don't have a very big dynamic range. You cannot detect, you can detect a very small quantity, but the large quantity saturate basically the system. So the idea is to go to some mix of analog magnetometer, analog squids to digital squids. With the digital part, you can get a bigger dynamic range, but you are not sensitive. You are sensitive to, let's say, 1 million times less. But on the other hand, you can get the dynamic. So if you combine both, you can try to do that. We did that with, in collaboration with Germany, with Fluxonics Foundry at my PhD in Jena, and with Limeno University as well. So you can see a digital squid where you have the pickup loop for the magnetic field. It's inserted on the chip. And you have here there is a small, it's only the digital part on this picture. You can see the digital system. I will explain how it works after, with a few Josephson junctions. Each of them is a Josephson junction, which has been used, and we used it in, so this is another picture where you can see more accurately. There is a digital squid here and an analog squid here, coupled to the digital. And if you combine both results, you can, when you put an analog magnetic field, you can see the digital signal and reconstruct totally this signal but in a digital way. The digitization here is done at liquid helium temperature at 4 Kelvin, so it's immune to noise, so it's very nice for, as you know, digital technologies solve a lot of problems and make also things cheaper. So we try to use it close to an analog squid in a shielded laboratory under the ground. You can see here, it's a commercial magnetometer, 3-axis, and we have some fluctuation that we fabricated with a ferromagnet close to the squid, so you can see the oscillation, and here you can see the digital squid oscillations, which are connected, correlated, of course, to the analog one. So we have something which works, but with a better dynamic range. It was a test in real environment. So when we had these this first system working, we decided to go to make a network of magnetometers. The reason is these squids are very good for medicine, but we also noticed that they can detect sometimes earthquakes, but before earthquakes, like 30 minutes, 15 minutes before earthquakes. So we see some signature in the laboratory which is installed in France, in the south of France. And but we can only correlate with earthquakes after, because we know where the earthquakes take place. Then we can correlate. The problem is when you see a signature on the detector, you don't know where it comes from, basically. And these earthquakes have frequencies which are very low, around 1 Hz typically. So the idea is to do triangulation, basically, to know where is the source of these earthquakes. We detected from France some earthquake in China, in India, in Turkey as well. So the idea is to try to get different detectors. We have one here in France working for more than 10 years now. We have another one now in South Africa working since 2012 already. And the third one is under development in Turkey, which is a very earthquake place. You know, there are many earthquakes in this area. And when we have these 3 systems, we hope we can correlate everything and get information, more information about the source. Okay, that was another application, geophysics. So I showed you a few of these applications. Now I'd like to come to the digital part. We can also, with the same devices, do processors and signal processing. These 2 examples of circuits. This is 5 mm by 5 mm. This one has been done in Japan. It's a microprocessor. This one has been done in the United States, in a high-press company. This is a signal processing. It's a digital receiver for military activities, for direct digitization of microwave signal in X-band for the military, for the Navy, and also for the ground army in the US. So these things, they do exist already. It's still some prototype, but they do exist. And the reason why we use this technology is first that we can go very fast in clock frequencies, 30 to 100 GHz. It's a state of the art today. Simple cells have been demonstrated up to the gap frequency of Naurium, which is good, you know, and we have no limit for that. If we change the superconductor, we can imagine we can go to about 1 terahertz, which would be very nice to have computer working not at 2 GHz but 2 terahertz, right? And so I believe really that in the next decade we'll reach this 300 GHz, at least for simple circuits. And another advantage is very low consumption. This is very important because all the limitation for the coming activities in the next 20 years will be made by energy. The problem is energy. It has always been energy, in fact, but it will become much more difficult in the coming decade. The application are already. I think most of the application in the future will be in the telecommunication domain. Analog to digital converters, which can take signals in the microwave range, routers and base station. I say mobile phone, in fact, it will be much more. When we see the development now of the 5G, and 5G is started, but 6G is already under study in some countries, and 7G and 8G after. So these systems, they will have potentialities which have nothing to do with what we know now. We will have autonomous cars, basically, so we need a very fast internet to have no latency, because they need to know where they are, to know if there are obstacles. So they need very high broadband internet, and they also need a lot of computing power, because when this system is when everybody will have an autonomous car, probably in less than 30 years, there will be a lot of data going in every direction. So you will need really a supercomputer per car, and energy is a problem. We cannot do supercomputers today in a small volume. Superconductors could allow that, and it's possible to do that with a few kilowatts, I would say with a few horsepower, say, which is like air conditioning in the car, not more. Semiconductor will have difficulties to do that with bandwidths of 20 gigahertz, for example. So telecommunication is a very important application, for sure, for the next coming years. Another one is security in intelligence. This is what is driving now the United States and China, is to have a strong computer to decrypt or to crypt data. But of course, if you have a computer who can do things that others can't do, you have an advantage, a technological advantage, and it will be really discriminating for between developed or developing and developed countries. So it's important. And science, of course, science has always been the main driver for technology. Usually science and the military, both. In this case, it's more military, but science is also interested. I told you about astronomy, geophysics. So in this case, when we take this Josephson junction for digital application, we use it in a different way. I'll just say a little bit about electrodynamics to explain why it's fast. When you take a Josephson junction and you forget about the physics, or you hide the physics behind the electrical equations, basically, you want to come back to Kirchhoff's law. Junction is just a capacitance because of the two layers, right, of superconductors, the capacitance. You have all the physics of the Josephson junction here, and there is also a resistance. We can model it simply as a resistance in parallel. I show you that either it's a normal resistance or it's a resistance that you add physically, electrically, when you fabricate the circuit. So the equations are very simple, right? You just have a current, it goes in three branches. You have Ohm's law, you have displacement current due to the capacitance, and you have the two Josephson equations, this one and this one, where the physics of Cooper pairs in the junction is hidden. When you check carefully these two equations, first I will not go into detail, but basically, you know, this second Josephson equation, it's related to the difference of phase of the wave function across the Josephson junction, and this is Faraday's law, basically. This is Faraday's law, it's the same. So Faraday, when he made his law, quantum physics didn't exist at this time, but it's still a quantum law. I mean, it's a law, we accept it, right? We accept it, we don't know why it's like that, but it's like that and it works. In fact, we can show that it's just, we can show it with quantum physics, at least in the case of this Josephson junction. So if you put all these equations together, you see that this Josephson junction, finally, it's a nonlinear inductance. Very nonlinear. You see the cosinus of the phase. This is what we call the Josephson inductance. It's just a value. Depending on the fabrication of the junction, it's connected to the critical current. This is fundamental constant. It is the quantum of magnetic flux. And here you see this cosinus is at the denominator. So it goes from 0 to 1 and minus 1. So the inductance goes from minus infinity to plus infinity. So it's very nonlinear. But finally, for electricity as well, you can replace this Josephson junction by a nonlinear inductance. And then you get something quite simple to solve, because everybody is supposed, at least at university level, to be able to solve a RLC circuit, parallel, if it's nonlinear. If it's linear, sorry. If you forget the sinus here, you remove this sinus, it's easy to solve. It's an oscillator, harmonic oscillator. If it's nonlinear, it's an harmonic oscillator. And you know, when you have RLC circuit, you have 3 time constant, RC time constant, LR time constant, and the plasma frequency, LC. You can get an electrical approach that you all know, right? The frequency, angular frequency is 1 over square root of LC, you have L over R and RC. And you can also replace these values by their physical meaning. Then you get a physical approach with the same constant. And when you see that, you see that this LR time constant, finally it's a value. It just depends on the superconductor you use. For niobium it's 0.15 picosecond, niobium nitride 0.07. It's very small. So it means it is a very fast system. This is typically the time of recombination of Cooper pairs in quasi-particle, or the contrary, quasi-particle into Cooper pairs. And this you cannot change. But these 2 values here, you see they depend on this ratio, CS over JC, square root, and here is linear. CS is a specific capacitance of the barrier. It depends on only on the properties of the barrier, on the dielectric constant, mostly. So it's the engineering of the barrier which will allow you to play on that. And so far, this is one of the weak points of this technology. We have a very good process with niobium, and it works so good that not many people try other systems. But we start to reach the limitations, and probably we need to have at some point some new barrier or some new smarter barriers, I would say, where we can play with this parameter. And this other parameter is a Josephson, where it's a critical current density of the junctions. This is also due to the barrier. Basically, it is connected to the fitness of the barrier and also to the density of state. Well, it's really intrinsic to the barrier. So basically, if you can play with the barrier, only doing some material studies on the barrier, finding new barriers, not new superconductors necessarily, but new barriers, then you can play with this parameter and you can play with this time constant, which are the limiting factors of this electronics. So when we go into detail, if we want to go fast, we want to have this 3 time constant. Well, maybe I should, no, I didn't put values, but when we check this 3 time constant, this one is the slowest one. It is limiting the speed. And the only way to increase the speed, and it was what has made IBM stop their activities of using these techniques in the 80s, because they saw that they could use this Josephson junction to do logic, but it was slow, 8 GHz. Well, 8 GHz in 1980 was really good, but today 8 GHz is not so good, and you had to cool at 4 Kelvin. It was complicated. And the reason was that this time constant was too high, it was too slow. So the way to solve that, what was proposed by Kyiv in Moscow State University in 86 about, was to say, okay, then if we cannot play on the capacitance because it's difficult, I mean you need to work on the barrier, but what is easy to do is to put a shunt resistor. You reduce the resistance. If you reduce the resistance, then you reduce the time constant. The problem is you will increase this one if you change. So there is a trade-off. And the trade-off is when you do the ratio of tau RC over tau LR, and of course the trade-off is when these 2 time constants are equal. It's the fastest way. So basically you need to do that for, this ratio is called Macomber parameter, it should be 1. Then when you have this relation, you can recalculate the time constant, you will just have 1, basically 1 time constant. And finally you can find a criteria to find the ultimate speed. The result of that is when you do this with this new system, you see that the state-of-the-art, with the state-of-the-art technology of 10 kA per centimeter square, you can go to 300 GHz with niobium. With niobium nitride you will be a bit slower because of the capacitance, which is a bit higher. But if you increase the current density, you can go a bit better, but you see, you saturate very fast. and it's very difficult to go in this range because the barrier is so thin that it's difficult.
I'd like to put a question. What is the operation temperature of your device? Because you show current voltage characteristic, which is very at zero temperature.
Yeah. We use it at 4 Kelvin typically. Well, it works well when you are below Tc over 2. From Tc over 2 to Tc, it gets worse because you have quasi-particles, too many quasi-particles. But below Tc over 2, there is not a lot of change between 0K and 4 Kelvin. A little bit, of course, there is some change, but you don't gain a lot. You can gain a little bit. And we try, in fact, to go the other way, to try to work at higher temperature. And that's the most difficult. 6 Kelvin, 7 Kelvin maybe in some cases should be the best you can do is now. That's the problem, in fact. We would like to go to high Tc is not useful for digital electronic, because if you are too high in temperature, you have thermal noise, then you get some error rates, digital error rate. Your circuit will always bug. So the only way, if you want to have low energy, is of course to have also low temperature. You cannot be low energy without low temperature. In any case, it's physical, and it will be the same for semiconductors as well. Nobody is better for that. Thermal energy is a general thing. So the only way is to find a good trade-off. 4K is a bit low because you need some cooling power, and cryogenic systems are good, but they are still very, very bad compared to thermal efficiency. So the trade-off would be 20K, I would say. If we can reach 20K, it's still good for digital electronics. We do very nice things. In the same time, for cryocooler, you could have a cryocooler of this size. You could put a computer in your pocket, which is already good because, I mean, the mobile phone were about this size as well, I think. So we are not too far from getting very nice system even on handheld devices, but still we need to change the material. We need to get rid of this now and get better materials. MGB2 is a solution, probably. PIC9 as well, yes.
You mentioned you have to reach 20K. Maybe so you're using conventional superconductors, but it's not possible to use unconventional superconductors in this case.
It is. What is really missing now, this technology with Naubium, it is so robust that everybody uses it. And finally, since it was very good and it was application driven, nobody put a lot of effort on going one step back, trying to find better things. Only a few people made it with GB2, Josephson junctions, and Squid, and it was very fast, which means it's probably a good candidate. After, whatever superconductivity, even high TC superconductors are just fine, but we need to cool them at 20K, for sure. If they are too high, they can work, of course, but not for complex application, for detectors maybe. So I think there is a lot of research to do on the materials. On the materials first, on the barriers second. And try to find whatever superconductor, whatever barrier, it should, if we can have a TC at least higher than 40K, then we can work at 20K. And then, I think we solve all the problems, and we will probably have a really much better application than semiconductors, because I don't see how semiconductors can get rid of these interconnects. Semiconductors have a problem with interconnects because they have fermions and they propagate charges. We don't have the same. We have bosons. We work with bosons. We don't work with charging devices. That's why we are better. And so yes, that's the point. So for the moment we are there. People push, and in particular in the US and China and Japan and everywhere, to go to 50. But you see, we get a bit, but not much. So we need to go now. Next research, I think, for the next decade should be on the materials and on the barriers, whatever they are. As long as you have a good TC, above 40K, there are not a lot of candidates, right? Only unconventional and MGB2 for the moment. And barriers, there is a lot of work to do, definitely. Not necessarily insulating barrier. Can be metallic, can be at the limit of insulator and metallic. We don't know. Okay. So in any case, when you have this junction, you can show that when you put an inductance, they can switch. When you put a current higher than a critical current, they can switch very fast, like 1 picosecond. And since there are this voltage pulse of 1 picosecond, which you see about, typically this is 200 microvolt, you have a very low energy, 1 million times less than semiconductors, and very fast. Semiconductors can also have very low energy transistors. They make them so small now, like 7 nanometer, right, or less. They can be very low energy, even lower than what we do. But the problem is interconnects. Interconnects, it is slow. There is no other way to escape. If there is a capacitance and a resistance, you have RC, time constant, and RC, time constant, is RC, time constant. You cannot escape from that. So we can compare the energy delay product, which is a very important parameter to check digital circuit. You want the operation to be fast, so delay should be very low, and you want low energy, so energy should be very low. So if you do the product, it should be the minimum. Sometimes you see publication with wonderful speed, but it takes forever to get the operation. So if it takes 1 year, if you have a processor which consumes nothing but works at 1 hertz of clock frequency, it's useless. So if we compare semiconductor with superconductor, we see that we are already better, and with a technology which is not as good and as expensive as semiconductor. We have big Josephson junction, like 1 micrometer size, 1,000 nanometer. Semiconductor, people work on the 7 nanometer. So there is a difference in terms of cost. So, and the circuit, well, they look like that. You have an assembly of Josephson junction. You see the resistance I told you here about to increase the speed. And when you see a circuit, it looks like that. It's an assembly of loop with Josephson junction and inductances, and that's it. And you buy the circuit. You have two kinds of loop, the small one and the big one. The non-storing one, it means when LIC is much smaller than that, then you cannot store a quantum of magnetic flux. So the information, this quantum of magnetic flux, it is a digital information, 1 or 0. It goes through, it cannot stay. But if you have a big loop, you can store the information, you have a memory, and you can put it again outside when you want. So you can do digital circuits very easily, just by assembling small loops of, well, you can count the junctions, right? Here there are 2 in this loop, there is 2 in this one. Typically you have loops with between 2 and 4 junctions, never more, never more. So as long as you can analyze this 4 kind of loops, 1 junction, 2, 1 is RF squid, 2 is DC squid, 3 and 4, and you can do everything. So to compare with semiconductors, I show you this Google. When you do a research on Google, it's processed by some machines, and these machines are on these buildings, which are always put along the river because they need to be cooled. This is the cooling system of the Google servers in Oregon, and you can see all these computers here, all these electronic boards. And in each machine you have this 1 chip of 1 centimeter square, which is 1 PC basically. If you put millions of PC and you correlate them, then you can have a lot of research at high speed. You can see the cooling system and you can see how it looks like. This is in Oregon in the days. You can see the cooling system here and the building with the computers. With a lot of energy consumption. And we need more energy. Now people want exascale computing. It means 10 to the 18 flop operation per second. We need it for climate change. We need it for fundamental physics. Sometimes to solve Schrödinger equation for complex systems. To understand subatomic physics. Well, there are a lot of applications, industrial and not industrial. So we need. We just just cannot continue to have computers which consume too much. So we need to find a solution. So now, this superconducting electronic, it is put on the roadmaps, international roadmaps, as a solution to replace semiconductors. And it is a roadmap pulled by semiconductor people. This is the first time since 2018 that it is put, because they don't see how to solve the problem. So this is one of the solutions. Only for supercomputers. For other things, they still have ideas, but for supercomputers, they don't see how they can escape the problem of the energy. Well, you know the limit of semiconductor. This is the clock frequency. Since you can buy this first computer in 85, 81, you see that in 2005, it's already 15 years now, but it has stopped improving, the clock, because of energy. And you can see the number of transistors. This is not up to date. Now there are 20 billion transistors per chip today. And the technology is 14 nanometer. The clock frequency is still low. Consumption is limited again for semiconductor by material problems. How to get good thermal conductivity of the chip to evacuate the heat, that's the problem. Superconductors are much better, there is no heat. So you can do 3D, you can stack them as many as you want. As long as you have a good process with planarization, you can do 50, 80, 100 layers. It's not a problem. You can take, there is no energy to dissipate. Semiconductors, they can do it. They have the technology, but the heat which is in the middle cannot escape fast. So it will, the chip will heat too much and just melt at some point. So it's the same with the two foundries which fabricate steel circuits. As you probably know, Europe has given up on the integration. Europe stayed at 28 nanometer, will not go above. Only the Chinese and American continue the race now. Only two left. And these are two foundries, TSMC for Apple, and the other one for all other machines. Android. Okay, so the reason of this heat is because when you increase the number of transistors, you increase the heat, so you need to reduce the consumption of transistors. And you cannot do forever, and you know, again, about 10-15 years ago, this power dissipation is limited to 130 watts. You cannot do more. It's a problem of materials now. Materials are the solution for semiconductors and for us as well. 47 minutes. Okay, so I can show you, I will show you that a bit later. There are a few technological processes for to design these applications. There are not a lot. The foundries, there is this one, MIT Lincoln Lab in the USA, which is the most advanced today. They can do 1 million resistor junction on a circuit. This is a foundry which is, how we say in French, ITARS. I mean, it's a technology control, technology export limitation. You cannot get the chips because it's sensitive. So you will never get access to this best foundry because unless you are American, and only inside America, not outside. There is a very good foundry which is nearly as good as this one, a bit behind now because of money. It's a Japanese foundry. We have a much smaller one because Europe didn't put a lot of money, so we're still waiting for to get Europe to understand the stakes, to put more money on our foundry, which has still, which is from experience of measuring devices from all this, is the most reliable. It's a very good quality, but it's not so dense. We cannot put a lot of devices per chip. And there are a lot of small fabrication facility at NIST in USA, at PTB in Germany, at INRIM in Italy, and in iPress. But I think iPress has stopped its foundry recently. Okay, also all these processes, so I can show you the best what is done now at MIT Lincoln Lab. You see the junctions of 250 nanometer, typically. Okay, which is the state of the art with current density of 10 kiloohm, and they can make 1 million junction working well. So it's very high quality process. By the way, it has been the boss of the foundry is a Ukrainian guy from Donetsk. This is a picture of the polarized process. You can see all the superconducting layers. You can see the resistive layers, and this is the Josephson junction here. It's not the last version. There are new versions with other inductive layers, but this is an example how it looks like. So it's very high quality. It's like semiconductor, no? And you can see here the junction area standard deviation as a function of the diameter. So for 1 micrometer, you are less than 1%, so it's very good. And you know, if you accept, let's say 5%, which is already it's still acceptable for digital electronics, you have a diameter of about 200, 300 nanometers. So you can already put a lot of devices on this chip, which is very nice. And now, if you compare, okay, this is performance of a supercomputer. It was in 2015 was like that. So you have the power of the machines and you have the energy efficiency, the number of floating point of operation per joule that you spend. And you can see all these points here. I'm not going to give the details. These are the 500 most powerful computers on this planet. They are all aligned. The reason, because they are all made by the same, by Intel. Intel fabricates 95% of the chips of superconductor in the world, basically. Competition was so tough, those are the only ones who escaped, who survived, basically. And the most powerful computer in 2015 was the Chinese one. I'm not going to give all the detail, just I want to say that if you want to have exascale computing, 10 to the 18 operation per second, with the present energy efficiency of semiconductor, you know, you go here and you arrive at 1 gigawatt. It's one power station, nuclear power station per computer, for one computer. So it's expensive for the electricity bill. 2017, okay, I will put this one. 2017, there is a bit of change already. It goes very fast. There is a new machine made by the Chinese, and you can see energy is the same, about 200 megawatt. Not 200 megawatt. It's about 20 megawatt. But they improve the energy efficiency. The Chinese, it's Chinese technology. We don't have access to these chips as well for the same reason that for the Americans. So they were the best in 2017. I don't have the last graph, but since last year, we saw the Americans have a better machine now. So the competition is very, very tough to get to this place. But what you can see is that you are limited by the power, and now you need to go to energy efficiency. You cannot continue to put more and more machines, otherwise you go vertically and you waste this power that you don't want. But what is interesting is to see what you can do with supercomputers, with superconducting supercomputers. You can imagine some circuits only with Josephson junction with 4 models. You take a small cooler that you can buy commercially with 1.5 watts at 4 Kelvin, 10 watts, you can buy that, and 100 watts, 1000 watts, they exist as well. This one, Europe is very good for the big machines because of LHC, they make big coolers. And you can calculate to make a supercomputer which does 1 petaflop per second and 1 you see exaflop per second to make exascale computing. How much power you need for the logic circuit, for the memory, for the interconnects, for all the mechanical parts. And in the end, you reach this computing efficiency here with the total power of the system. And when you put that on this graph, you are here. These are these 4 points. And you see the energy efficiency of these machines. They don't exist, it's just development now. But it is, the energy efficiency is about 50 times better. It's not 1 million times because you need to cool as well, so there is a price to pay to cool. There is a factor of 1000. And also, I mean, between one Josephson junction and a complex circuit, there is, you lose a lot. So, but basically, if you are realistic with an engineering approach, not scientific approach, engineering approach, you can get this exact scale computing here with, you see, 1 megawatt. It means you can have such a big machine like this big Google server in a small room, just in a big cooler of 1000 watt. It's not a big system. You can have it at home. So it will be also less expensive in the end. And this system which we can already do are here, so you can see how the power is less. I mean, it's 10 kilowatt, it's very little to get a petascale computing, so you can run it already on your desk nearly, which is nice, and there are intermediate versions. So this is where we are. I'm nearly finished, and you probably heard, I've just finished with these 2 slides of quantum computing, because the future is quantum, right, as is said often. Quantum computing is not just superconductors, it's also optics, and probably optics will win. I believe optics will win. You can do quantum computing and not Boolean computing with just a sun junction as well. Just there is a problem, you need to cool the system at 20, 30 millikelvin. And if you want to have 1 watt it's not a lot, 1 watt, right? At 20 millikelvin, you need 1 gigawatt at 300. I think you need 1 nuclear power station. And in fact, this is with the state of the art. But in fact, it's not even true because nobody knows to make 1 watt at 25 millikelvin. Nobody. It's just a rule of thumb, right? But today, the efficiency of cryogenic system at 20 millikelvin is 10 to the minus 9 of Carnot efficiency in reality. So it's very, very low. So for application, quantum computing is great for, it's very nice to attract and for science and a lot of things. But for application, we need to wait 50 years probably, and we need to have to solve this problem of temperature with superconducting qubits. So it's not clear yet if it will happen one day, we'll see. But the good thing is with superconducting qubit is you can do artificial atom. You can fabricate your quantum system, and very nicely. But if you want to have it to work, you need to have quantum correction codes. And what is not said by people who fabricate that, like IBM, Intel, Google, is around when you have a system of 10 qubits, all around you have hundreds of thousands of just sun junctions. And this needs a complex circuit. So you need to fabricate this complex link to cool them. And that will be very difficult to do at 20 millikelvin. So there are some difficulties and advantage. The other solution is to go with optics, optical qubits, like how it's called, color centers, these kind of things, quantum dots. This is probably easier because you can work at room temperature. The difficulty is you are with a real system. And you cannot choose your, for example, if you want to have a 2-level system, you don't choose your 2 levels. You have your valence, your color center, and you have your 2-level system you want, but you have also all the crystalline field around, and you cannot, you cannot separate the 2 levels you want from a complex environment. So they will have difficulties as well. It's another solution. I believe it's easier in optics than in superconductors. But we'll see what the next 30 years will tell us. And in any case, it's a very exciting field as well for students to go, because there is a lot of development, not only on Boolean superconducting electronics, but in quantum. There are a lot of opportunities in the world, in Europe as well, to get PhD students. We have money to take PhD students. We don't have PhD students today. And we have, in Grenoble, they hire 20 PhD students. It's a simple topic.
The junction must be identical. How you check this point?
Yeah, but that's, this quantum, they say quantum, so it looks nice. All the problems are under the carpet. For sure, it's very difficult. What they do is to have, you have a quantum, you have a qubit, and you have a digital qubit, and it's not the same. To correct this qubit, you need a lot of physical qubit to get a real digital qubit, and it can be hundreds of them. So you need a lot of electronics, quantum electronics around to make it work, and with quantum errors, correction codes. And this makes it complicated. That's why 1 qubit is not just 2 junctions. In the end, it is 2,000 or 20,000 junctions. Because you need to do statistics, right? Quantum is statistics, basically. You need to do measurements many times, and you need to correct, and then it will take time as well. And decoherence time is a problem, especially at 25, that's why we put down, right? 25 millikelvin. So you need to do this operation very fast before the qubit coherence disappears. So yes, all these problems are not solved, and when you discuss with the people of TH and Zurich and people who really work on it, they really don't know how they will do it. So we are in a field like politics is in front, and scientists, we don't listen to them, but one day it will go the other way. We had the same problem with ITC, right? So when they were discovered and you saw the moon, right? You do everything, electrical trains, and in the end there was nothing. Because it was so exciting that politics came before science, and maybe scientists they pushed to get to sell these things, but in the end you have the consequences after. So I think we need to be careful with qubits. We may have consequences as well. We need to be very careful about how to do and check very objectively the performance and not hide anything. This quantum superiority or whatever words that I see on the abstracts, we'll see. I'd like to see, yes. But for the moment we are not yet ready. So I finish with that. I compare the 3 technologies. CMOS, it works. 2.4 gigahertz, 300K, 10,000 megaflop per watt. Superconducting processes, it exists. No memory yet, but digital works well. We lose a factor of 100 in temperature, we gain a factor of about 15 in speed, and and also 15 energy efficiency, very good. Qubits, well, we don't know, I mean, it's not brilliant, we cannot compare. We just know that it works at 0.04K, right? Still, again, a factor of 100. The maturity is much lower. We have billions of transistors in semiconductor, millions in superconductor electronics, and just thousands with the D-wave electronics, 1,000 qubits. And it's not quantum processor, it's just quantum annealing, it's a bit different. So we still have, I think the most important when we compare this superconductor is this factor. I mean, Carnot breakthrough are probably in the materials, as I said, should work on the materials and the barrier. I'm sure this is the future. And the other point is thermodynamics, not electricity, not electronics, thermodynamics. How to make a good system with very high Carnot efficiency. Can we use thermodynamics at the nanoscale? Should we do quantum? Well, go directly back to the statistics and not stay with thermodynamics to find other ways to do transformations. That is, the difficulties, I think, they are really here. And in some way, it's easy to say, the people who do the coolers are much behind, right? They cannot produce 1 watt. I mean, they are just... and the reason is a lot of engineering, it costs a lot of money, and if there is no market, there is no money to develop. So we are like with a pen and chicken and egg problem. So probably there is some work to do on the thermo, well, I cannot really talk about quantum thermodynamics, right? It's statistical physics and quantum physics, but we need to work on these thermal issues at the nanoscale, even at the atomic scale. And we need to work on the barriers, and it's also atomic scale things. And if we can solve these two, maybe we'll do something here, but it's not yet clear. Oh, thank you. Maybe it was a bit too long, it's 1 hour. Thank you.